for the current model, we've assumed a constant delta x, and we haven't stated it, but we've sort of implicitly assumed a constant delta y, so that all these intervals have the same area. All these little rectangles will have the same area, delta x times delta y. It isn't necessary to do that, but for brevity and convenience, we've done it here. Whether our delta y's are all the same or not, we have assumed that our delta x's are, so that we can factor delta x out of this sum. Delta x occurs in every term of this sum. There are m terms. Every one of those m terms contains a delta x, so that our delta m sub I equals delta x times the sum from j equals 1 to m of our density evaluated at xi star yj star times our delta y. This sum, leaving out the delta x for the moment, this sum, if we allow our delta y's to approach 0, is going to approach an integral. It's going to approach an integral with respect to y, and if we understand the process of forming an integral, we see that that integral is going to be the integral of delta of x sub I star times y dy. This is going to be a y integral. Our yj's, our delta y, are going to become just a plain y and a dy. So let's write that out. Now, first of all, let's correct one little thing here. Our delta m sub I is approximately equal to this sum, so that we're saying that our mass on the ith x interval is approximately equal to the sum that we get when we partition the y interval. Assuming that our x sub I star gives us an accurate gives us a point at which we can accurately sample our density with respect to the x variable, we can proceed to let our y intervals approach 0. And we'll then get something resembling an accurate approximation to the mass within our x subinterval, rather than mass corresponding to our x subinterval. Now, let's write out this expression. Again, delta m sub I is delta x times the sum from j equals 1 to m of our delta density, delta x sub I star y sub j star times delta y. This is an approximation. We get a better approximation if we take the limit as delta y goes to 0 or as m goes to infinity, whichever we prefer to think of. The limit of this sum of density evaluated x sub I star y sub j star delta y, well, this limit becomes an integral. The integral of our delta function, our density function, evaluated at x sub I star y dy. Remember that this limit affects only y. It's only the delta y that's approaching 0. Our x sub I star is still a sample point within our ith interval. But now we've smoothed out all the approximations according to our y sub j's and our delta y's, and we have this integral. Now, what are the limits on this integral? Well, you'll recall that our partition for the y went from 0 to f of x sub I star. And we can even take another look at what we mean here. We've partitioned this strip in the y direction, and the partition runs from x equals 0 on the axis up to a maximum of f of x sub I star, so that the limits in this integral are from 0 to f of x sub I star and following the lead that we established when doing partial derivatives, when doing this integral, our x sub I star is going to remain constant. Our y is going to vary, so in the process of integration, we're going to be integrating this function as a function of y with the assumption that our x remains constant. Note that when we substitute our limits then into the integral, those limits are going to be substituted for the y values, and there's no reference to y in either of these limits. Both of these limits, one of these limits is 0, the other simply depends on x. So that this entire expression will become just an expression in terms of xi star when we sum our mass increments from I equals 1 to n, corresponding to our partition of the x-axis from 0 to 1. Any y reference will have been integrated out in this process. So now let's consider what our total mass would be. So total mass is the sum from I equals 1 to n of our delta m sub i's. Delta m sub I is this expression, so our total mass is the sum from I equals 1 to n of, I'm going to reverse the order, I'm going to put the delta x after the integral, but I'm going to put parentheses around my integral. Okay, so I have the integral from 0 to f of x sub I star of delta x sub I star y dy. Running out of room here. And now I wrote times dx, and that's wrong, so I'm going to have to fix that. I'd like to do more elegant fix, but I'm just going to have to kind of smear over it. I can't patch that very well. In any case, it's going to follow that our mass, our total mass, which I'll represent by capital M, and I'm afraid that's kind of off the picture here, so I'm going to have to slide this over. Our total mass M is going to be what? It's going to be the limit as our delta x goes to 0 of this expression. Now write out the expression and hopefully get the whole thing. So it's a limit as delta x goes to 0 of the sum from I equals 1 to n of the integral from 0 to f of xi star of density at xi star y dy delta x. Now it's our delta x that's approaching 0. So our x sub i's are going to be squeezed into tighter and tighter intervals. And our sum is going to approach an integral with respect to x, where our xi's simply become x's. So that this becomes an integral of an integral. The integral is the y integral. That goes from 0 to f of xi star, but now that's from 0 to f of x times our density. Our x of i's are now squeezed into just plain old x's. So we have this inner integral with respect to y, very similar to the one we had here, except again our x sub i's are squeezed down, and our delta x becomes dx, and we only need to figure out what our limits on the integral are. This entire process started with a partition of our x interval. Remember that our original function ran from 0, x equals 0 to 1, so that we partitioned our interval from 0 to 1. Our original region then goes from 0 to 1, and our x interval runs from 0 to 1. Recalling that for our specific example, f of x was 2 minus x squared, and our density function of xy was 1 over the square root of x, 1 over the square root of 1 plus x plus y squared, and I'll write that down in a minute. We get a final integral from 0 to 1 of the integral from 0 to 2 minus x squared, our f of x function, and that's an integral of 1 over the square root of 1 plus x plus y squared with respect to y. This integral, remember, we're going to get an antiderivative here, and then we're going to substitute 0 and 2 minus x squared for the y's in our antiderivative. This is just going to become a function of x, and then this is multiplied by dx, meaning that this integral, this definite integral, will then be integrated from 0 to 1 with respect to x.